again. So the density matrix is actually a sum of individual product matrices. So let's say that you've got only one spin, right? And this spin is in the state x. We call this state x. And x equals 1 over square root 2, 1, 1. So this is the state x, okay? And imagine now you have another spin that is in the state y.
I don't know if will that. I think you can write a superposition, just a state that's a superposition of two states, and they'll have cross terms, will they?
I'm not sure what you mean.
Are you saying that no one state can generate terms can generate coherences?
No, what I'm trying to say is that if you're taking the density, so imagine you're taking the density matrix for only one spin. It doesn't make sense to do that. But imagine you're taking the density matrix.
I think it does.
Okay, I'm not sure enough in that matters to know. So the density, let's call this rho star. The density matrix corresponding to this guy would be this one everywhere. Okay.
That has coherences, even though it's not.
This has coherences because there is only one spin. We're talking about one spin. But the density matrix we're talking about in NMR is about a huge number of spins. Okay. And imagine now you have all your spins in the transverse plane, but in a non-coherent way. So you can have like x, y, or any state that corresponds to any angle in the plane. Okay. So you're going to have like lots and lots of stuff. And actually, you will always have in your density matrix, you will always have 1 and 1 here, but you're going to have exponential minus I theta here, exponential plus I theta here, and you're going to sum them up all around the place, and it's gonna sum up to 0.
No, but Wendell, the reason I don't think this addresses the question is that if you have a single spin, right, that still has to obey the properties where the trace has to be 1 and the coherence is going to be anything. The trace of that has to be 1 and the coherence is going to be anything. So basically, the fact that those coherences are 1 would make it so that if you sum up all 4 elements of those matrix, you would get a non-zero. You would get something that's not 1, right? And so I think her question is, why don't those coherences matter? Like, why does it not matter what those are? So the whole point is that each element in this matrix, in her conception, corresponds to a population, or the amount of the wave function, the amount of the wave function that is in each of these states, right? And so the total, there's a finite amount of wave function, right? There's a 1.
I'm not sure I would like to quantify
the
amount of wave function.
Well, but
it sounds like a really but you always define them as 1, right? Because
it's basically if a particle exists, it has probability of 1 in being in any of the states that it can be in the
universe. Yeah.
Right. So what that means is the sum of all the possible states that it can be in has to equal 1.
Mm-hmm.
Right? So what that means
basically the coordinate, like the sum of each coordinate.
Right. But so her question is, why don't the coherences matter? My answer to that is that basically the states are the diagonal, and then the coherences just are a measure of how much mixing there is.
That's the right answer
in that basis.
Yeah, that's the right answer. Yeah, I'm sure.
Okay, so the off diagonals are only telling you like the dynamics of your system. Doesn't really tell you like.
Well, it's not the dynamics. It's what it is. It's the orientation of your basis in the state, right? So you can diagonalize. I think there's any matrix that represents a real particle or a wave function can be diagonalized. I know that's true, right?
Yeah.
So come again.
Any matrix that represents like a density matrix or anything like physical can be diagonalized, right?
Yeah, it's even stronger than that, because every matrix that represents every density matrix is actually Hermitian.
Right.
It can be diagonalized in an orthonormal basis.
Right. So what that means is that there is a state there is a way to write this matrix. There's a basis to write this matrix in which you have zero terms on the coherences, and the numbers in the coherences correspond to how far off how far you've rotated your frame, your basis state, in some n-dimensionally large space. So
in order to complete that, I would try actually say if you look at the density matrix that corresponds to the x eigenstate here, if you actually you can actually diagonalize this matrix, and the transformation matrix is going to be Ix, basically. Sorry, no. It's going to be rotation. The transformation matrix will be a rotation around Iy, which transforms Iz into Ix. So it corresponds, and then the matrix would be 1, 1, 1 minus 1. Well,
1, 0.
It would be normalized, basically. I would have to think about it, but yeah.
So I guess then I have a further question. If you do that, if you transform the bases, after you have some coherences, will then the trace still always be 1?
It always has to be.
The trace
the trace is independent of whatever base you're looking at.
So another way maybe to think about why the coherences don't matter in terms of the traces is that so what the density matrix tells you is Sx, Sy, Sz, and they don't commute. So you can get information at most about one of them, and so you define this particular density matrix that tells you S of Z, say, and so S of X and S of Y, you can't definitively get any information about them, so they don't really affect the probabilities.
I guess that's actually a very good point. That the way we've been showing this today, I guess, in the last hours, seemed like this property got ignored. But it's a very, I guess, important property to keep in mind that we don't know what Ix and Y are if you
Right. As Gwendol said, you can define the density matrix, so it tells you S of Y instead, and it's just conventional to write the density matrix so that it's quantized along the magnetic field because it makes things simpler.
All right. Well, let's just continue to tomorrow. Okay.
Okay.